Our Notes Unit 2, Section 7, Emission and Absorption Spectra. This is part 2, where we look at spectra. We're going to begin by considering what's called the Bohr model of the atom. Niels Bohr was a physicist, and his name is given to this model of the atom which he developed. Well, in Bohr's model of the atom, we begin with something you're probably familiar with, and that's the nucleus, where you have the protons and neutrons. And the electrons around the outside in the Bohr model exist in certain shells or energy levels. I'm just going to center the nucleus slightly there. There we go. So what you find then is that electrons can exist in the Bohr model only in certain allowable energy levels, or as they call them in chemistry, shells. We'll call them levels in physics. They're a little bit like sort of circular orbits, a wee bit like planets going around the sun. Okay, they're all supposed to be concentric. So this is the nucleus. And all of these are allowable energy levels for electrons, because as you know, electrons orbit round the nucleus. What Bohr hypothesized was that the electrons orbit round the nucleus, but they can't go, anywhere they like. He argued that the rules of quantum physics only allow them to exist in certain energy levels and not between them. And that's quite crucial. Now, when we're drawing these energy levels, it's a bit inconvenient to have to draw the circles all the time. So what we do is we just draw a small section of them, and we just draw them as flat lines. So something like this, for example. So if we begin with the lowest energy level, which is called the ground state, so we'll call that energy level 0, or E naught. Now on the actual atom, this would be E naught. Okay. And that's the ground state. And in a hydrogen atom, for example, that's where the single electron would normally be. But it's possible, if you give the electron energy, to get it to go up to a higher level. So, for example, up to what's called the first excited state, or E1. Now, in our flat diagram, we'll draw E1 sort of maybe there between those 2 points. Okay. So that's E1, and that's the first excited state. And by excited, we mean that the electron has more energy than it has in the ground state. It's received that energy from somewhere. It's possible for it to receive even more energy and to go up to an even higher energy level. this would be E2, the second excited state. So that would be E2 there. And of course, there's an E3 as well in our diagram, so let's pop that in. You tend to find the energy levels get closer together the higher up you go, which I've tried to show in my diagram. So there's the third excited state, or E3. So, let's imagine that we have an electron sitting quite happily in the ground state, which is where it kind of would normally be. It's possible that if the atom absorbs some energy, usually in the form of a photon, so say a photon comes in, then this electron can be promoted up and goes to the first excited state. It's got more energy up there than it has lower down. Generally speaking, when an electron is promoted, as this one is, it's often called an upwards transition. When it's promoted in this upwards transition into a more excited state, it's very often unstable up there. And so what tends to happen is it will spontaneously fall back down again, seeking out its lower energy level, which is the natural tendency of systems to go to a lower energy level. And when that happens, a photon is then released. And it will have energy E. Now, just going back to the promotion of the original electron, that could happen by absorbing a photon. It can also be excited up to the first excited state by being heated. If you heat the substance, the heat energy can give the electron enough energy to be promoted. It can even happen by placing the gaseous version of the substance in a container and putting a very high voltage across it. That can also excite the electrons up. In any case, if we imagine the electron falls back down, then the photon energy E, well, that would equal HF, as you know. Now, that could be the absorbed photon or the emitted photon. If we focus on the emitted photon for a moment, then that E, which equals HF, so let's pop that in, HF, that's going to be the difference in energy between E1 and E0. You just basically take the difference in energy levels to get the energy of your photon. And that's the important equation for these spectra. Okay. So, basically, if the photon is absorbed, then the electron gets promoted. So this would be this scenario. So your incoming photon there would have energy HF, which would have to equal E1 minus E0. And if that incoming photon has precisely the energy difference between the two levels, that energy is given to the electron, which promotes it. And this is what happens and leads to absorption spectra. So these absorption spectra are the visible spectra, full visible spectra with the black lines in them. And the black lines show where light has been absorbed. If, on the other hand, the photon is emitted, then that happens because the electron falls to a lower level rather than being promoted to a higher one. So what's going on when you have a photon emitted would be this. So your electron's been promoted already somehow, but it's unstable there, so it falls back down. And when that happens, a photon is emitted. Energy E equals HF, which is again E1 minus E0. And this is what happens in emission spectra. So this is obviously the absorbed photon, and that's the emitted photon. Going back to our original diagram, when you get up to the top of the higher energy levels, the levels get very close to each other, but you eventually come to a limit. There's only so much energy that the electron can have, and the highest energy level that it can have right at the top there is called the ionization level. If an electron reaches the ionization level, then it is actually free to leave the atom. And of course, when an electron leaves an atom, you have a free electron, and the remaining atom has become a positive ion. Hence the name ionization level. And that's the highest energy level that can be reached. And of course, you lose your electron if it gets up there. It's quite common to get questions about the number of possible transitions. Often comes up in multiple choice questions. So say you've got your energy levels like this. Yeah. If you were asked how many possible downward transitions are there, well, let's imagine that's E0, E1, E2 and E3. Well, the easiest way to do it is just to start at the top and say, right, if an electron were at the top, where could it fall to? Remember, it can't fall in between levels, it can only fall 2 levels. So that one could fall to there. So there's one possible downward transition. But it could, in theory, fall down to that level. So that would be number 2. Or it could fall all the way down to the ground state, and that would be number 3. So those are all 3 possible downward transitions from level 3, the third excited state. But if we started on level 2, second excited state, where could we go? Well, we could fall down to level 1, first excited state, so that would be the 4th possible transition. Or, of course, we could fall down all the way down to the ground state. That would be the 5th possible transition. So that's starting at level 3 and starting at level 2 exhausted. But of course we could start at level 1. There's only one place we can go there, and that's down to the ground state. So in this particular example, there are 6 possible transitions. I've shown 6 possible downward transitions, but each of them, of course, could be a possible upward transition if you just reversed the directions. Now a little look at the hydrogen atom. The hydrogen atom is the simplest of all atoms. It's only got 1 proton and 1 electron, and it's got a number of possible energy levels. You find that when you get to helium and beyond, the energy level diagrams become very, very complicated, but in hydrogen they're a bit simpler. So let's imagine that we've got our ground state here. So that's E naught, and maybe we've got E1 there. Now I'm going to miss out all the other ones, right? But at some position up here, you're going to have the ionization level. And in between there'll be quite a few lines which get closer and closer to each other as you go up. Well, something interesting occurs here because we've got to decide where the 0 level is. And by convention, the 0 level is the ionization level. Now you might think that's slightly odd, but that's the way we do it. And what that means in a hydrogen atom is that because as you go down to lower levels, you must have less energy. You obviously have more energy in a higher level, less energy in a lower level. Well, if we say our 0 joules level is the ionization level, then it means that when we go lower than 0, we have to become negative. So you find out, and these are real figures, that in a hydrogen atom, the ground state is at minus 21.76 times 10 to the minus 19 joules. And the first excited state is minus 5.424 times 10 to the minus 19 joules, and so on, and so forth. So if you were asked, what's the energy of the photon released when an electron in a hydrogen atom falls from the first excited state to the ground state? There's our photon released, E = equals HF, which is E1 minus E0, the difference in those two levels. So this photon energy then now when you calculate its energy, it's really important that you put all the numbers in exactly as they're presented. So that has to be minus 5.424. Take away minus 21.76. And all of that, of course, is times 10 to the minus 19 joules. And when you do that, you'll get 16.3 to 3 significant figures times 10 to the minus 19 joules. So that's the energy of the photon that's released. And of course, you could then work out the frequency of that photon using E's HF. Planck's constant is h. And then if necessary, you could get the wavelength of the actual light by using V as F lambda. Well, that brings us to the end of part 2 of 2.7, emission and absorption.